Today we're going to be talking about implementing a custom search syntax using Solr, Lucene, and this cool thing I found called Parboiled. First things first, hi everybody, my name is John Berryman. I am a search architect and I work with Opensource Connections. I come from an aerospace background, but soon along the way I found out that the two most key things that I loved were programming and math. So I've tried to pull that as much as I can into my new work, which is Solr and big data stuff. Please check me out on Twitter. That's probably the easiest way to get back with me. I look forward to any advice or any feedback you have regarding my talk. My Twitter name tag is pretty much my name, John Berryman, with all the non-phonetic characters removed. So anyway, getting back to implementing the custom search syntax. So today we're going to talk about the example problem that I had with my work with the United States Patent and Trademark Office. For this particular project, we were building the future of patent search for the Trademark Office, and who knew that the future of patent search would at least partially be re-implementing a search syntax that was already 30 years old. But they wanted to pull things into modernity. They wanted to use a technology that wasn't slowly dying away. And so this involved basically building this old search syntax so that it would interface with Lucene. We'll also talk about more specifically, the search problems that examiners face. When an examiner looks at patent search, it's a very, very different problem than you're used to with like e-commerce. We will talk about unleashing the full potential of Lucene. What you get on the surface with Solr gets you a long way towards the type of behavior that the patent examiners want, but we actually had to dig down and get some other things that are available only in Lucene. We will then talk about how we actually created the new parser itself. It's using something that I think is kind of unique, kind of a new way of doing parsing, and I'm very excited about it. And then we'll take everything that we've learned and put it all back together, and I will show you how you can create your own Solr search component. Hopefully then we'll have a couple minutes left over for questions as well. All right, so digging right in. Let's talk a little bit about the project and give you kind of a background for why I would do such an audacious thing. In 2011, we started a project with the United States Patent and Trademark Office called Patents End-to-End Search. And the goal with that project was basically to prototype the next generation of patent search that is used by examiners during the examination process. We worked on this project until early 2013 when we got sequestered. There was a lot of financial issues with the government earlier this year and recently as well. But fortunately, this project is coming back online soon, and rather than prototyping the solution, we are actually now being asked to build this as a final production approach. So we're very excited to see that the changes that you'll see here, these new ideas, are going to be incorporated, and patent examiners will be using this shortly. One of the specific goals that the patent examiners had was to upgrade from this kind of old and dying technology they had to something that is got a lot of user base. It's broadly applied, and of course, since we're here at a Solr conference, that is Solr. It appears to be a good choice for the work that they're doing there. To give you a little overview about what the project looks like, this is kind of our data flow, and this is how everything is wired together. Now, the most important aspect for us is this top row right here, where we get from the patent text itself into Solr, and we serve it up through our API. This part, even just getting it into Solr, aside from the search aspects I'll tell you later, was a tremendous ordeal. There are, I believe, 10 million patents as of now that are not OCR'd and like so old that they're just like images or in a file bookshelf somewhere. So of these 10 million patents, the data is not in a very consistent format. So we have the predecessor of XML is some of the earliest documents. I think it's SGML. Anybody? Yeah. And then once we finally moved into XML, they didn't quit there. Every few years that they would decide, well, we need to incorporate something else. So we have several different patent types. And in order to deal with this issue, we used Tika, which is also used internally within Solr. But we had an external Tika process that we augmented with our own modules to understand, oh, this is that type of document, and it goes through this slightly different pipeline. And this was a really good approach to normalizing all the data so that finally Solr gets a consistent set of fields, and the data within the field seems very consistent as well. Within Solr, we kept not only the text of the patents, but also the text of the classifications. Part of that was to join these two together to make sure that the patents had the correct classification information inside of it. But also the classifications were held themselves in their own index because we had to refer out to that regularly. The classifications are very complex for patents. Classifications alone, there was one file that described the hierarchy of classifications, and that one file had 100 megs of text, and that was just one file to describe all the classifications. So pretty complex there. The other stuff I guess I can go over just real quickly so you can get the full scope of the project we dealt with. The patent images themselves came to us in giant multi-page TIFF files, and we had to chop them up and convert them into PNG so they could be presented on the web. And for this task, I'm still not convinced this was the best solution, we used Bash. So Image Magic, I think we ended up going to Graphics Magic. A lot of exciting stuff there. Shoved them all into S3, and that's that we used for basically to serve the static documents. All this is bound together by our JBoss API, which not only talks to Solr and not only talks to our image server, S3, but also uses a database to track user history as they search through stuff, and also serves a few static files. Now, the static files themselves are the app. So we went gung-ho with this whole JavaScript-based web app approach that's becoming more and more popular now. And this is, I can't quite remember the name of the JavaScript library. It was not my part of the project. But you get everything that you'd expect here with a search app. At the top in the middle is a search box. The middle part right here is the document results that have been very customized. Even though it's not exactly the best picture, on this right side over here, you get facets. Top left, you get the user history. They're actually using old searches and aggregating old searches together to create new, very large, complex searches. And on the right side, we have a palette where the examiners put the documents of highest interest as they're looking at a particular case. So given an overview of the project, let's dive in and look at the specific search aspect of the project. Now, for the average user of search, and probably even for many of us if we deal with e-commerce, we're used to search pages that look like this. Basically, you have the text box at the top, you have the documents, you have facets on the side that have a count, aggregate counts across every value in that facet. I called this paradigm a needle in a haystack paradigm. It's kind of trite, but it makes a point. Basically, you're looking for something, a black dress shoes or something like that, and once you found that something, you leave, pay for it, and you go away, and that's your search experience is done. Patent examiners are a little bit different. So they kind of invert this process. Given a new patent application, the examiner must prove that this does not exist in any prior art. And practically, you can't prove the non-existence of something without going through all of the documents and checking off that it's not here, not here, to here. So practically what this implies is that the patent examiners are doing a lot of time, doing a lot of work creating kind of canvases of queries that help them mentally slice and dice the data set to understand kind of the topology, the grouping of the information within that particular domain. And once they have a set of documents that they believe the prior art might possibly be in, then they exhaustively go through that much smaller set and basically read over every patent and say, okay, I have done my due diligence and I have not found any evidence that this exists in patents already awarded or in non-patent literature, which can be like academic proceedings and stuff like that. Now, historically, this involves, the patent examiner's experience involves a lot of constraints. And they're okay with this because it's just what they're used to. They don't use facets, which is odd because I just was talking about how they slice and dice stuff. That's facets, right? But they do it all with queries. They don't use synonyms in the Solr synonyms.txt sense. But they do use synonyms in that they will type heart attack or myocardial infarction and they'll actually make queries that themselves represent synonyms, and then they'll combine queries together to actually get the behavior they want. There is no stemming, so you'll have, along with those synonym queries, you'll have people that type in all the different verb forms that they might run across, which is a pain. And the most unusual thing to me is that they don't use relevancy sorting. What they do is they keep asking different questions until the data set is not too big and not too small. And once it's tens or maybe small hundreds of documents, they'll say, good, I'm done with the search part, and now I'm going to read through all the documents and make sure it's not here, which is unusual to me, but that's how it works so far. So because of all these constraints, examiners are very dependent upon a rich search syntax. And the name of that syntax, this is the 30-year-old syntax, is BRS. No one remembers what that stands for, but that's what it is, BRS. And it's our job as the Solr consultants to re-implement this for them and make it function with Solr and Lucene. This is the big point of the talk. So now you're probably thinking, why not just use dismax? I mean, that's easy, right? Dismax, we have a simple syntax. So there is no syntax. You just type words in. It understands what fields you might be looking for, so you don't have to worry about fielded search. And it's all relevancy sorted. They don't want it. And so this kind of goes back with what I said on the last slide. They're not scared of really complex search syntax. We'll look at that in a second. They want the fielded search because they want to be very exacting in how they're searching through the documents. And oddly enough, they don't care about relevancy sorting. Politically, there's another factor. They already know BRS, and it's easier for them to just keep going with BRS. So since we're stuck with it, let's take a look at what BRS entails. BRS has fielded queries. You can tell it which fields to look in. BRS is the simplistic Boolean search. You've got ands and ors to put pieces of your queries together. BRS, this is probably the most outstanding and unique feature. You have very, very precise proximity-based searches. So you can ask for words A that is in the same paragraph as B, or C that is with D in the same sentence, or E that is adjacent to F in order matters, or G that is near H, but it doesn't really matter where the order is. So, and also there's parenthetical grouping. So this nests arbitrarily deep. So you might use this BRS syntax to build a query that looks like this. You might say, I want to look for any widget that is directly before the word gizmo. I want this match to be in the same paragraph as doodad. This thing has to be in the description field. Their fields are after rather than before. And also, all the documents that come back have to have thingamabob somewhere in it in one of the default fields. So that's an example, and we'll come back to that example later. All right, so unleashing the full potential of Lucene. So out of the box, Solr gives you the ability to make position-based queries. But you're kind of limited to phrase queries, right? So I could say, you know, quote, give me some query tilde 4, and then I get, you know, those words spaced 0 to 4 tokens apart, something like that, right? But if you peel back Solr and look deeper into Lucene, you actually have a whole branch of query types that provide a much richer palette for making position-aware queries. If I had it to do over again, I'd probably rearrange these bullets here. The most important bullet is the span near query at the bottom. This is your basic building block. With a span near query, you pass it a bunch of subqueries, which themselves might be terms, span term query, and you can say that these sub matches, be it terms or more complex queries, must be in the same unit, same area with slop, which is kind of like phrase slop of some amount, and order either matters or doesn't matter. And based upon that, you can build things that are a lot more complex than phrase queries, because the most obvious thing is with a phrase query, you can't nest phrases within phrases. There are some pain points. There are some big pain points, actually, with this span query. And the biggest one I ran into is that a span query is a query, a Lucene query, but a Lucene query is not a span query. So there was definitely times where I wanted to build a span query with an array of normal Lucene queries, but the two family trees, if you will, do not cooperate. There is a JIRA issue to resolve this and to merge these two branches, but that hasn't happened yet, and I haven't seen any work on it in the past several months. So, all right, so let's take a look into the SWAN operators, same with adjacent and near, and look how we might implement this using Lucene. We're going to use a position gap strategy. And the thing that we're really going for is specifically the same and the with operator. We need to somehow encode the information of this is a sentence and this is a paragraph. And the way we did this was by sticking position gaps into the token stream as we analyze stuff. So prior to the analysis, we need to have an understanding of what the biggest sentence is. And really, there's going to always be some obscenely long sentence. So maybe the 99th percentile sentence, we'll say that sentence is 50 tokens long. So we need to at least have that in mind. And similarly, we have to understand which paragraph or how many sentences are in the largest paragraph that you could sanely think of. And we'll say 50 again as an example. And so during analysis, we're going to suck in the text, detect the sentences, and every time we get to a period, simplistically, then we artificially add 50 blank tokens. So position gap is 50. And then every time we get to something that indicates a new paragraph, we artificially add in there a position gap of 500, which basically what we're doing is we're ensuring that if I want to look within the same sentence, all I have to do is look for a query that is within the same, within 50 tokens of each other. And by default, that shouldn't ever be overlapping two sentences. And if I ever want to say look for something in the same paragraph, then I want to say look within these 5,000 tokens because I know we've got a big blank chunk of 5,000 tokens after it. So this is kind of a simplistic way of getting at it. There's a couple of competing ways that we actually did this, but this is probably the easiest one to represent. So now since we've done that, we can use these span near queries to build up the idea of same with adjacent and near. Let's see how. All right, so this is a Java class, and everything in here is going to be static. I'm sorry if it's just a little bit small. But basically, I'm going to use the static methods in this class to give me the simple idea of same with adjacent and near. For the same query, I take two queries that are span queries, left and right, and I create a span near query that takes these two guys, make sure they're within max paragraph length, 5,000, and the order doesn't matter, so false. Very similarly, with takes two queries left and right, make sure within the same sentence length of one another, and order doesn't matter. Adjacent, make sure there's no length between them. Order does matter, and near is the same thing except for order does not matter. And that's our whole palette of new and unusual BRS operators, the so-called SWAN operators. So this class is actually going to be pretty useful for later in this talk. now since we have encapsulated the idea of same with, near, and adjacent, we can just call out to this class later directly from the parser to construct our queries. All right, so next up is Parboiled and Parser Expression Grammar Parsing. It's a mouthful, so it's called PEG parsing. So you need, if you're going to parse your own syntax, then you're going to need a parser generator. And probably the biggest names in this area is Antler and Java CC. And as a matter of fact, someone verified this for me, but I think the query parser in Lucene is Java CC. Is that true? It's true. Okay, so these tools are fine, but in my opinion, they carry some baggage with them that can be a bit unsavory at times. You have to have an external syntax definition file, extended Bacchus-Nauer form, something like that, and this always kind of sets aside from the rest of the code. And whenever you want to make a change in how things are parsed, you change this special exalted file. You have an extra compile process, and so it's, there's now an extra step in there when you actually have to make changes. And so the risk that you kind of run is creating kind of untouchable, like holy relic code. Someone built this query parser syntax. Everyone here reads Java, but no one reads this syntax, so we're not going to touch it. So it's a little complicated. Now, I ran across Parboiled. One of my colleagues pointed this out to me when I started this and said, John, you don't know anything about Java CC or Parboiled. Might as well look at Parboiled and see what you think about it. It's interesting to me. And I found out that as I learned about the parsing process and what all is involved, I think Parboiled is actually pretty neat as well. Parboiled is a Parser Expression Grammar parser. And a Parser Expression Grammar, PEG, is similar to a context-free grammar, except that there is no allowance for ambiguity. Now, fortunately for us, not too many programming languages have ambiguity. So PEG, in my understanding, is just as complete as CFG for describing programming languages. And as an example of that, Parboiled can itself parse the Java syntax. So we're talking about building pretty complex stuff here, potentially. This is a lot richer than, say, regular expression grammars. There is no external syntax definition. Rather, instead of creating this auxiliary kind of sacred relic file, the code that you write to parse, the syntax that you write for the document that you write that describes the syntax is itself the code that parses the syntax. It's one file, it's Java, and it runs just when everything else runs. And I think that's the coolest part of it. This needs another bullet. It just doesn't have it. Parboiled at this point is also pretty fast. I think it started as kind of an experiment to see what could be done. And at this point, I think a little bit after I finished playing around with it, it's apparently gotten quite a bit faster. I don't really know how to quantify that, but supposedly it's fast. It was definitely fast enough for our work. So let's take a look at how easy it is to put together a simple syntax. And apparently, I was never a computer science major, but apparently whenever you go through this class, whenever you're talking about parsers, you always do the calculator parser, and this is it. But take a look. It's pretty easy. When we run through this, I'll run through really quick, going down deep into the syntax, and then I'll build back up slowly. I think it's a better way of kind of putting everything into order. With a calculator, at the top level, you have expressions. At the next level, expressions are made of terms. Terms are made of numbers, and numbers are made of digits. Okay, so back up. Digits are characters ranged from 0 to 9. Reads like English almost. Numbers are sequences of digits. And in particular, this is a little bit unusual syntax, but once you've matched one or more digits, once you have that match, then you can call the Parboiled match function and get whatever that match is, which is a string at this point. You can parse it as an integer, and you can push it onto the parse stack, which, as we'll see when we get back at the top, I've templated this class by integer. So everything on the parse stack is an integer. So I can push anything that corresponds to that. Going up one level higher, a term is composed of numbers. But there also might be 0 or more of these clauses. For instance, there might be 0 more of a multiplication sign and another number. And there might be a number, a division sign, and a number. And so let's take the bottom route. If you have a match on number, division sign, and number, then all we have to do is this is not match, this is another function that you have, but you can pop off whatever was matched at the lowest level. I'm popping off one below the top of the stack, dividing it by popping off the top of the stack. It equals some number, and so I'm pushing it back into the stack. And without belaboring the point any further, it works very similar for the plus and minus operators. In this real simple example, you can basically see how you can do order of operations with division and multiplication at the deepest layer and addition and subtraction at the top. And to run this thing, it's really not that hard at all. These 3 lines are a little bit cryptic, but they're only 3 lines. First line, you create the parser. Second line, you run the parser against the input string, which we're just using the standard input. And the third line, after the parser has run, you take the result from the parser, you get the root of the tree, and then you have access to this value stack that we've kept pushing and popping from, and you get the top level of that value stack and convert it to string, and you've got the output. And that works. It's kind of cool that I can write a Java class, and I don't have to do any other extra steps. It just works. Okay, let me grab a drink of water real quick. So next up, we'll be talking about putting it all together in Solr. All right, so are we ready? I've made this simple little checklist to see if we're ready or not to build our parser. First of all, we have to have an understanding of the BRS syntax. And we understand, although it's very small, we understand that it's composed of ands and ors, Boolean search, and also these extra swan operators, same with adjacent, near. So we understand. Next up, does Lucene itself have the inherent capability to parse these type of queries? All right, we built a class that actually provides static methods that do exactly that. So check. Next up, do we have something available to parse the syntax? And I've just talked about Parboiled, the peg parser. So check. And finally, do we have something that we can package this all together and configure it? And Solr provides all the functionality that you need for that, and this is what we'll talk about right now. So check. So now since we're ready to get parsing, there's several pieces that we have to put together. The first thing is the swan parser itself. This is going to look a whole lot like the calculator parser that we did in the last section, and we'll step through it as well. This middle bit is some basically Solr boilerplate that we need to create a new request handler and interface it with Solr. Middle part is building it, which is really simple. On the right side here is configuring Solr to work with it. And finally, we have just one real quick example where we're using it. So let's dive into the parser itself. So this is a class called the Wimpy Swan Parser. The original class was called the Swan Parser, and it was a lot longer and a lot more boring to read. So this is kind of everything pared down to the most basic implementation of what we used for the Patent Office. I'll go the same route as I did earlier. I'll read top to bottom and then build it back up. At the top level, you have queries. Queries are composed of OR expressions. OR expressions are composed of same expressions. Same expressions are composed of with expressions, and with expressions are composed of, these are operationally on the same level, adjacent or near expressions. Expressions are composed of terms, and terms are composed of characters. Okay, so back to the top. Characters are any of these things. Pretty straightforward. A term is one or more set of characters. Also pretty straightforward. And we're using that same syntax again. Once I make a match, I can pull out that match, cast it to a a Lucene term, or create a Lucene term with that, create a span term query with that, and push that onto the stack. So everything on this stack, rather than an integer, is going to be a span query. Adjacent near expressions are a sequence of a term and some of this stuff. So there's a lot of nuance between, do we have the keyword near? It's not as simple as a plus or minus sign. Does it matter if the people using it capitalize or lowercase, or how many spaces and stuff are in between it? And so simplistically, what we did is I created a function that's, you can look at later. It's actually on the screen. It's just way down there, where I said near is any of those things. There's a little extra syntax. So when you see near, that is basically just the operator. So an adjacent near expression is a term followed by 0 or more of these, near plus another term, for example, or adjacent plus another term. Whenever we match one of those things, term apple adjacent banana, then we can pop off banana, we can pop off apple, we can use our class that I described earlier with all the static operators, and grab a swan query near operator and create a new swan query with these two subqueries, which this is itself a span near query. Push it back on the stack, and we're ready to go up a level. So very much the same stuff. Adjacent near builds up to with expressions. With expressions build up to same expressions. Or expressions. There's also and expressions, but that I actually omitted that because it gets into the kind of the pain point that a span query is not a query, but a span query is a query, but a query is not a span query, that issue. So that's why I have silently omitted and. But anyway, we're back at the top. In order to, so far so good. Does that basically make sense? It should be fairly straightforward. So now to hook this into Solr, it's not much harder. Basically, this is all boilerplate. We want to create a QParser, so we extend Wimpy Swan QParser as a QParser, and it's got just a couple methods in here. The first thing is constructor. Actually, looking back over my notes, I'm not exactly sure why I've got that here, because I basically did nothing. But there is the parser, which you've got to fill this out. During the parser, I'm going to create the parboiled parser using that class I just defined. And this is very similar to the main class I showed earlier. I'm going to take, this is the special part right there. Every QParser has QSTR, query string, in itself. So I'm going to take that element and run the query parser on that guy and get out the result. And if you remember from the last slide, all these, whatever we have in the value stack is nothing but span queries. So this works well. A span query is a type of query. And so I pop it out, cast it to the correct thing, and I return the query. And Solr is ready to go with just a normal span query. There is a wrapper that you have to put around that in Solr that extends the QParserPlugin. Basically, this implements a factory method. Not much here. You have an initialization class. For the simple example that we've talked about today, I do nothing. For the actual patent examiner work, we looked into the schema here and pulled out like the default fields. And so that's, if you notice, we didn't mention fields in the other class either. And the last little bit is create parser. And this, all it does is creates the parser, the object that was above this. Compiling, jarring it all up is pretty easy if you're using Maven, which you probably should be. Maven package packages this all up into a jar. You can copy the jar into your contrib folder, or I think as of now there's a lib directory that you can stick it in that's sibling to the data directory. So I'm sure either place will work. And then in configuration, this is the final bit. All you have to do is create this new line that says, "Hey Solr, we've got a new query parser. It's called Swan, and it references this class that we showed you from the previous slide." Not presented here. obviously, in order to detect the sentences and the paragraphs, you need some special analysis chain to do that. That's outside this talk, and it was also fairly ugly code, so that'll suffice. And then once that's all in place, start up Solr. Solr is now aware of the new Swan query type, and using it is simple. This is just the URL. You just say def type is Swan, and then you say the query is whatever. And this is the exact query that we used earlier, and it works. So it was, after a little bit of a learning curve, it was actually surprisingly easy to put together your own customized parser. All right, so that wraps it up. Please do connect with me later. John Berryman on Twitter. I would love to have some feedback. And it appears we have about 10 minutes left for questions. So if you got questions. So if you weren't able to hear him, he was talking about, as presented here, we added a position gap between sentences and a really large position gap between paragraphs. And his idea was maybe as we're parsing through the sentences, we could delimit sentences with a special token and delimit paragraphs with another special token. I say that that's a good idea because that's actually the way we did it. So we were wrestling around with both of these ideas when we built this for the patent office. This one ends up being a little bit more performant because the query that you have to make to include, the span query, look for anything that's in between these two sentence delimiters. That ends up being a more complex query, so it's harder to present, and it's also was a little bit less performant, though it was never bad enough to deter us from using it. So at one point, both, but we ended up actually using the one that didn't present here. So great question. Yes. Question was, if the query syntax itself is malformed, then what does Parboiled do? And, oh, well. All right, never mind. So, Prezzies are neat. So the question is, if the syntax is weird, what does Parboiled do? It does the right thing. There's 3 different types of parsers that you can build. So you create the syntax in one of those files, one of those classes. And then you create a parser with that class. And if my memory serves me correctly, there's 3 different types. One that runs super fast, and if it runs into the error, it just dies catastrophically and shoots you the bird. All the way to like the most rigorous class will run, check the syntax. If you run into an error, it actually, and I never grokked this, it'll actually allow you to attempt to recover from whatever weird syntax error you have. And I think the middle one at least just throws appropriate errors or something like that, rather than just gone. Thanks, guys.